Welcome back, Adventures. Hi, and today we are here at day 13. I know I'm a little late. It's 10:30 p.m. and I'm almost one whole day late, but well, sometimes life gets in the way. And today I'm presenting you from a tridecagon camera for day 13. And well, if you're new here, I'm Jatin Kumar Malik. I'm a principal engineer who really enjoys solving these puzzles, and every year I just wait for it. Last year I did a whole blog post series on Medium, and this year I'm doing YouTube. So if you haven't seen yet, check out my day 1 to day 12 videos in this spoiler free playlist here. And I hope you enjoy solving these problems. So let's get started. So today we are at day 13, and in 27 minutes we will have a day 14 problem. So since it's a Friday night, I'm going to make some coffee, and probably after I solve day 13, I'm also going to do day 14 in a go. But let's get started. So day 13, today's problem is called claw contraption. Let's read that. So next up, the lobby of a resort on a tropical island, and this is a reference to 2020 day 24 problem. The historians take a moment to admire the hexagonal floor tiles before spreading out. Fortunately, it looks like this resort has a new arcade. Maybe you can win some prizes from the claw machines. Oh, remember those dreadful machines where there is a claw hanging and you can pick up some toys and win? Let's read on. The claw machines here are a little unusual, obviously. Instead of a joystick or a directional button to control the claw, these machines have two buttons labeled A and B. So writing down, so we have a claw machine and we have two buttons. So we have A and we have B. And you cannot just put in a token and play. It costs 3 tokens to push button A. So there is a cost given for both of these buttons. So T here is nothing but a token. Let's read it. So with a little experimentation, you figure out that each machine's button are configured to move the claw a specific amount to the right along the x-axis and a specific amount forward along the y-axis each time a button is pressed. So usually how it works is, like, considering this is an x-axis and this is a y-axis, usually you have like a joystick where you have 4 directions, and then your claw starts somewhere from here, and then you can move it somewhere on the x-axis and y-axis, and then when you press a button, it goes down and picks up something. But here it says that we can see, like, when you press a button, it's moving a specific amount on the x-axis and specific amount on y-axis. So let's read more. Each machine contains one prize. So this claw machine has exactly one prize. That seems a little less. And to win the prize, the claw must be positioned exactly above the prize on both x and y axis. So this claw, this prize has a coordinate x and y wherever it is placed. Like, so if you're looking at this, it's an example, wherever it is placed, you need to get your claw exactly over the prize to get the prize. Yeah, makes sense. So you wonder, what is the smallest number of tokens you would have to spend to win as many prizes as possible? And you assemble a list of every machine's button behavior and the prize location. That is our puzzle input. For example, so we are given this example, and you can see that we are given, like, if you press button A, it moves the claw by this much. So like if I press the button A here, it moves like X by 94 units and Y by 34 units. So considering it is starting like this, so 94 and 34, and if it is X and Y axis and claw is at 0, 0, it will basically go ahead and move to this direction. And similarly for button B, we are given another one, which is X moves by 22, Y moves by 67. And we are given the coordinates for our prize, which is here, which is X is 8400 and Y is 5400. And similarly, like, we are given different machines. So there are multiple machines. So this is machine number 1, 2, 3, and 4. And what we have to find is, we have to find what is the smallest number of tokens that we have to spend. So remember, the token cost is given here. So every time you hit button A, you spend 3 tokens. And every time you press the button B, you spend 1 token. So ultimately, we have to find like the minimum number of token so that you can win this prize. And the list describes button configuration and price location of 4 different claw machines. And I think this is just explaining the problem. And let's look at how this will work. So I'm just looking at if we are given an initial position of X and Y. The price is located there. So initial position 84 units. Yeah. So like I think that is implied that the initial position. So if you have a claw, you start with 0, 0 for each machine. Yeah, so let's look at the first case. So we are given a scenario where our initial claw position, so if I pick a color, the initial claw position is 0, 0. And now starting from this, we are given these 2 buttons. And remember, whenever you press button A, it costs 3 tokens and button B costs 1 token. So it is saying the cheapest way to win the prize is by pushing the A button 80 times and B button 40 times. And let's see how that works, because remember we are given also the positions here. So if your X was initially 0 and Y was initially 0 at T is equal to 0, let's see what happens when you do TA. So TA means that you press A 80 times. So which means that your X position will move forward 94 by 94 80 times. And similarly, your 34 position for Y will move forward by 80 times. So let's see that. So I'll do some quick calculation. So 80 into 94 is 7520. So after 80 presses, you will be at 7520. And if you look at Y, we can see 34 into 80 is 2720. So Y will be at 2720. And our target position is the price position, which is 8400, 5400. And let's look what happens if we press B. So B is now 40 times, and we are going to increment by the value that is given here. So that would be 40 into 22. So 40 into 22 is 880. So I will add 880, comma, we will do the same thing for 67. So 67 multiplied by 40 is 2680. So I will write 2680. And if we sum both of these values, because we are just pressing them and the order really doesn't matter, we can see that the total comes to 8400, 5400, which indeed is our price position. And based on this value, we can calculate the cost that it took us. So the cost, remember, for A was 3 tokens and for B it was 1 token, which means that you will have to pay 80 into 3 tokens plus 40 into 1, which is 80 into 3 is 240, 240 plus 40 is 280. And for the first machine, that you will have to minimum pay 280 tokens to win the prize. And similarly, in the example, we are given here that for the second and fourth claw machine, there is no combination of A and B presses that will ever win the prize. So actually there are conditions there for second and fourth machine. No combinations of increment by these values that are given here will lead you to the price that is here. And that is very much possible, right? Because you are always moving at a fixed interval and they are all additive in this example, like the examples we are given. So you can imagine, like, if your price is here and you're always moving ahead by a fixed interval for A and for B, if that window is bigger than the last delta of that price, there will never be a way for you to reach that. Simple mathematics if you try to plot it. And for the third claw machine, I think they have given another example here that the cheapest way to win a prize is to push A buttons 38 times and push B button 86 times. And you can do the same thing where you can calculate, you can multiply 38 with 17 and 86, and then you can multiply 86 with 84 and 37. And when you add that to 0, your total should come to this. I'm skipping that, but you're welcome to try that. And then when you multiply A into 3 and into 86, the total tokens is 200 tokens. That is the minimum amount of tokens we have to do. So the most prizes you could possibly win in this set is 2. So that is the first one and the third one. So at most we can win 2 prizes. And the minimum tokens you will have to spend to win 2 prizes is 480, which is the total of 280 and 200 air. So to win this, you need to at least get 480 tokens. Okay. You estimate that each button would need to be pressed no more than 100 times to win a prize. So that's basically the classic constraint we are given. We are given that like for both buttons A, comma B, for each you would not be doing more than 100 button presses. So this is what we call like a constraint. So the idea is that you would try to get your answer within 100 tries, and if you cannot, you would exit and you will say that there is no way to solve this puzzle. And figure out how to win as many prizes as possible. What is the fewest token you would have to spend to win all the possible prizes? And if we look at our puzzle input, we can see that we are given a bunch of claw machines. And if I close this and move back, the idea is that we would look at each claw machine one by one, find the minimum number of token as long as we don't exceed 100 button press. So that is the constraint. And as soon as we find our answer, if we find our answer, we calculate the cost and we move on to the next machine. And let's say if you cannot do it within 100 constraints, you skip that and you move on to other machine. So that's the problem. It's a very, very interesting problem. And I absolutely love solving problems that resemble real life problems. But this is a bit tricky because instead of freely moving the claw, you have math to do that. And that seems to be the theme from last couple of days. I think a lot of maths related problems. But with that, I think now is a good time for you to pause the video here, grab a copy and pen, write this, and try to see like how you will solve it. And I have already given a hint that this is not a coding problem. This is a mathematical problem that we are going to write code to solve. So give it a thought, pause the video here. And once you're back, and I will discuss some of the hints in terms of how I am planning to approach it and how do we convert this mathematical problem into our coding constructs. Yeah, so if you're still here and you're looking for a hint, let's talk about that. So remember I just mentioned that, so I'm going to write hints with this red color today. Remember I just mentioned that we need to express this into math. And by math, I mean it needs to be expressed as an equation. Remember those? We used to have those linears and polynomial equations in your elementary maths and I think also in your senior year. So if you think about this, the problem is fairly simple. You start with your claw at 0, 0, and your final x and y position of the claw needs to be over the prize, which basically means it needs to match the prize x and y coordinates. And we also know that with each button moves, how claw will move along the axis for each machine. And that's different, right? That we can see here. So we have the behavior that is given and it's encoded into the machine. So for each machine, we can set up two equations here. So if you look at this, we could have like a underscore x multiplied by a plus b underscore x multiplied by b is equal to p underscore x. And I will explain what it means. And similarly, a underscore y multiplied by a times plus b underscore y multiplied by b, and this should be equal to p underscore y. So this is nothing but this is our prize coordinates that are there. And here we are saying that a is the number of button press that you are pressing the a. Let me write it down. And b is the number of button presses b. So number of button presses, right? And then your this ax and bx are basically the coordinates that you have to increase the number by. And in this, you have to fill these values, and that should probably help you to get closer to this. You just need to find, can you get to this or not? And here, if you see, the tricky part is that your a underscore x is like the what value the number is increasing by. And then you need to find a pair of a comma b that satisfies this equation. Does that help you think about how you will solve the problem? And of course, if you have an equation and you have in both the equations, you have two unknown variables, the fastest way I can think to solve is, because we are limited that the number of button presses will always be less than 100, I think for the part one, we can definitely go with a brute force approach without doing much. And by brute force approach, we means that we can just run a loop that will validate the values of a comma b for each combination from 1 to 100 to see that if there is any combination where the value of the p underscore x and p underscore y would match the value of exactly our claw. And this should be fairly fast to do that in this case. And if you think about the complexity of this is a linear equation. So our complexity here would be more or less O of n, which is the number of times you would run the code. So looking at a comma b, where you are going to try these number of combinations, this should be a fairly simple thing for even your old beta machine to run. And we will basically find all the combinations of a comma b that we can find. And once we find the combination, remember we have an equation where our a costs 3 tokens and b costs 1 token. All we need to do is we need to calculate the cost for each combination, which is 3a plus b, to find the cost. And whatever is the minimum cost we get, we take that and we exit and we move on to the next one. So with that, I hope the problem is clear to you. And what I'll do is I will start to write some code, and maybe you should also do that. And once we are back and we have the answer for our part 1 puzzle, we will discuss about the part 2. So all the best. And hey folks, hi, we are back. As you can see, we have solved the part 1 and we have received 1 gold star. And if we had to do a retro, I did not do anything other than what I discussed here. So I just modeled these both equations for x and y coordinates. And then when iterating through the loop, I just solved them and I just got like the minimum of the cost that I got and like the new cost. And as I got the minimum cost, I just returned it. And in the outer loop, I just maintained a sum of it. And that's how we got the minimum cost. And I think having the number of button presses less than 100 really helped because we could brute force it. But with that, let's move on to part 2. And let me make some space here. Don't worry about the answer. I'm going to blur it. Let's use the green color. We'll say part 2. And let's read it. So as you go to win the first prize, you discover that the claw is nowhere near where you expected it would be. Due to a unit conversion error in your measurements, the position of every prize is actually... Okay, I don't even know what that number is, but let me see. So this is 1,000... million, billion, trillion. Is it 10 trillion? It is 10 trillion actually, yeah. So it is actually 10 trillion higher on both an XY axis, and trillion is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 10 raised to the power 13 high on both X and Y axis. I don't know what that means, but it definitely means that brute forcing this is going to be hard. So now you add 10 trillion to X and Y position of every prize after making this change. The example above would now look like this. So I think, remember that example above that we had? So the example now says it looks like this. So initially we only had 8,400 and 5,400 and 12,000 and 12,000 and 7,000 and 6,000 and 18,000 and 10,000. But now we casually have just added 10 trillion to that because prices are actually like, it seems like they are on the farther end from our starting claw position. And now it says that it's only possible to win a prize on second and fourth claw. So with this updated test case, this is the only one where you can win a prize. And there is no case for the first one and fourth one. And unfortunately, it will take many more than 100 press to do so. Of course, because after 100 press of A button, we are only moving by 2,600 and 6,600 and 6,700 and 2,100. So we have to get closer to 10 trillion something, right? And sadly, they have not given like what is the answer of these test cases. So probably our code should first try to solve for that. But let's see. Using the corrected prize coordinates, figure out how to win as many prizes as possible. And what is the fewest token you would have to spend to win all possible prizes? And let's look at our puzzle input again. So it hasn't changed, but it says here that using the corrected price coordinates. So it's very clear that we will need to first update this file by adding 10 trillion in front of everyone. And that's going to be interesting. Okay, so we'll do that. And once we do that, we'll have this case here. And I think now is a good time for you to pause and think. I'm sure you're also probably laughing looking at the scale of the problem. And once you come back, we will discuss about some of the strategies that are going in my mind. And then we'll try to see how to solve it. So yeah, grab a copy paper and try to see that how we can work over and build over the solution that we did for part one. And is there any optimization or any way for us to do it for part two? Yeah, once you're back, let's discuss more. And yeah, welcome back. So let's discuss about how would we approach this. And again, like for just laugh and gigs, I'm going to definitely try brute forcing this. But you can clearly see that even if we are increasing the x by an order of 100 here, which is 10 raised to the power 2, getting anywhere close to 10 raised to the power 13 will at least involve us hitting the button 10 raised to the power 11 number of times, which is basically the number of operations that we will have to do. And clearly brute forcing is not going to work unless you have access to a quantum computer and like some 100 qubits. Google recently launched their Willow. Maybe it would be fun if any Google engineer is trying to solve advent of code on that. I'm not sure if that's even a thing. So let's think. So let's try to visualize the problem. I have realized that it's always good to do that. So if we assume that this is the x-axis and this is the y-axis, and this is 0, 0, where we are starting from. And of course, this is huge. Initially, our price was really close, and now our price is somewhere here. So we have p, x, y that is given to us. And let's take this example. Maybe it is 10 trillion and 8400 and 10 trillion and 5400. Now, what comes to your mind? Obviously, because if it's C, now if I try to zoom here on the bottommost edge, and if we start traversing, let's take a blue color maybe, it obviously doesn't make sense to traverse using these units, which is basically only 94, 34, 22, 67 for X, and this is for Y. Sorry. So this is for X and this is for Y. It is just going to take a lots and lots of time. So what I'm thinking right now is initially, I'm very, very sure that there is going to be a very simple mathematical solution to it. But sadly, my math is not really the strongest suite. Surprise, surprise. And especially, I think after engineering, I haven't really seen math. I am really good with calculating the time complexity and the order of growth functions. But when it comes to basic, proper math, yeah, let's say I'm just average and that's how it is. But at least I'm aware of that. But thinking of that, I think one thing that comes to my mind is that since we are solving it at a one claw puzzle at a time, and our buttons are hard-coded with the equation that we had. So remember, we had, let's say in this example, we will have 94 into A plus 34 into A. And then similarly, we will have 22 into B plus, not plus, comma. So comma, comma, and then this would be 67 into B. And this here will be our X coordinate. This here will be our Y coordinate. So what I'm thinking is, can we use some heuristics? And if you think about this problem, we already know that we have to get to X and Y. It doesn't make any sense for me to try like first few, not even 1,000, first few 10 raised to the power 11 values, because that is just a given, right? And maybe we can just iterate over that. So what I'm thinking is there a way that, and if you look at this, what I need to do is I need to find values, basically like a bounding box. Actually, it doesn't even need to be a bounding box. All I need to do is I need to find some values that gets me very close to this number within a margin of error of like few hundred delta, right? So like by using some arbitrary values that get me closer to this edge and get me closer to this edge, I can get there and I can then restrict my scope of the problem to solve for only the values that fall inside here in this particular area, where this would be, if you have to build it, it would be x dash comma y dash, x1 comma y1 comma x2 comma y2. And even this seems like a very large number, but considering that we have a very precise number here given 10 trillion and 84,000 and 10 trillion and this thousand, I think what I'm thinking is first I can just try to get close to 10 trillion number, both on our x and y axis, because we are just adding that. And then I just need to solve for delta on top of that. Now, obviously, we will not get to the perfect whole figure of 10 trillion because we are incrementing by 94, 22, 34, and 67 based on the number of prices. But maybe that can help us get the answer. Like get as close as you can, and then it's a matter of calculating the function. If you press X, you go up by 94 and 34. And if you go out of bound on either or, you do a backtrack and then you try to press B. And if that doesn't work, you do a backtrack and then try to press this. So you will have some combinations of A and B, but they will both have like a common delta. Like to get here, that number would be fixed. And we can call that like our base presses. That you have to do either way to do that. Interesting. Like I'm just trying to think how many solutions can this have? Because when we were limited by 100 values, we had a constraint to exit. But here I don't see any constraint that after these number of presses, you can exit. Which means we can now have an absurdly large number of combinations even to reach this base position of 10 raised to the power 13. And why is that? Because if you look at this, A is 94. When you press A, you move by 94 and you move Y by 34. And then when you press B, you move X by 22 and Y by 67. So this means there is a way where you can first quickly gain on X by pressing a lot of A while not moving a lot higher on Y. And then you can start to press B where you are moving quicker on Y by 67. It's almost a magnitude of 3 times faster than X, and then get to this position. So then there is another case where you will do a lot of spam of B to get higher first, and then you will start pressing A to get and converge to this point, which is our price. And then there are actually like a lot of cases in between as well. But yeah, I think this is a good hunch and this is a good place to start with to solve this. And I can't really think of any other position. I'm thinking here, even if we do recursion and we do some kind of a memoization, all the cases are different and all the sums that we are doing in each machine is different. There may be definitely cases where you can reach to a same point. So let's say I was talking about here where you're pressing a lot of A first and then pressing a lot of B. There can be some cases where you first press a lot of B and then you press a lot of A and then you meet here. And then from here, there is always one path that is covered. So probably memoization can still help us a little bit. And with that, sadly, I don't have any other hint for you because this one is a real head scratcher. So what I'm going to do is I'm going to jump into my VS Code and I'm going to give this approach, like this is like a greedy approach, a try where I will try to get as close as to the price value within a bounding box. And then by going up and down, I will try to figure out like what would be the most optimal cost. And yeah, with that, I think I'm going to leave you to try and write some code yourself. And I will do that as well. And don't worry, once I solve the part 2, we are going to have a retro where we will discuss about what approach did we took and like how we can further optimize that. And with that, I'll see you in a bit. Hey folks, welcome back. As you can see, finally we got the another star for part 2 of day 13. And I'll be honest, it took me over 1.5 hours to solve this. And it took me on a journey that I haven't really been after my engineering days over 10 years ago on mathematics. And I got to learn so much today about this problem, and I think the approach that we were discussing here, that quickly became very complicated for me to solve. And then I just basically started writing on my trusted old journal to see how we can simplify these equations, and it's very interesting, like, trust me. So I'll show you how I worked on it. And if we can open the problem again. So I think what we are most interested in looking at this equation is that we can simplify this equation into that we need price of x will always be equal to our the button A. So button A underscore x multiply by A presses, and plus our button B underscore x multiply by B presses. And similarly, I'm just simplifying this here and this here. So similarly, our price of y would be here equal to our A underscore y multiply by A presses plus B underscore y, multiply by B presses. So I'm just simplifying this, that if I want to calculate x, I need to multiply something with 94 and 22, which is this. And if I want to calculate y, I need to multiply something with 34 and 67. So we can write this as this simple. And then it struck me that this is basically a problem of two equations with two unknowns. And it is called something. I could tell that based on my engineering mathematics that this two equations with two unknowns is called something, but I couldn't remember it. And I tried searching for it, but I kept going in the wrong direction. So I just sat down and I thought I'll simplify it. So now if the only thing that we need is we need to solve for this A and B here. We already know AX, BX, AY, BY, PX, and PY that we can see from here, which is 94, 34, 22, 67, and then 8400 and 5400. So now what we can do is we can simplify this equation for one of the things. So maybe I'll try to solve this for B here. So solving the above equation for B, it comes to, so it's very simple. So this comes to price of x minus this whole thing goes there. So minus A underscore x, I'll do some bracket, multiply by A, and divided by our this B underscore x. And similarly, I can simplify this equation right here also for this B. So then this becomes our py minus this ay into a goes there. So a underscore y multiply by a divided by b. So I'll write it again. So divided by b underscore y. And you can see where this is going, right? Like, so basically we solve both equations to get the b. And now we can eliminate this b because they both are equal to b. By the relation, we can then say that they both are equal to each other. And when we do that, so let's write it down. So px minus a underscore x multiply by a divided by b underscore x is equal to this thing here. So py underscore a underscore y multiply by a divided by b underscore y. Now what we can do is similar to how we simplified for b, we can now, since we have eliminated b, we can now solve this equation for a. So now solving this, that becomes by comes here, bx comes here. So this becomes b underscore y multiplied by bx minus, I think you multiply this with this. So b underscore y multiplied by a underscore x multiplied by a, and then this equals to the same thing here. So py into b underscore x. So this goes here minus, you do the same thing where you write a underscore y multiplied by a multiplied by b underscore x. Yeah, so we can simplify this to a is equal to b underscore x multiplied by, multiplied by py minus b underscore y multiplied by bx divided by, the other way around it would be b underscore x multiplied by a underscore y. So a underscore y, and then minus, similarly, b underscore y multiplied by a underscore x. And this gives us an equation for a. And now the beauty of this is that we already have all of the values given that we can fill here, given into our puzzle. So here we have ax, ay, bx, by. So ax, ay, bx, by, and then we have px and py. And if we solve for that, and if we get like an integer value because we need to have an integer value to calculate the number of tokens. Our tokens that we are inputting and the button presses that we are doing, they cannot be fraction in the real world. So if we get this integer, what we can do is we can take that value, whatever we get from here, and then we can put this value back in one of this equation. So we have two equations. And when we put that value in this equation here, if we get another integer value, that becomes our answer. And it took me a while to understand that in this scenario, there will be exactly one solution based on how our input is entered. And this is a typical Eric Wall's Advent of Code special problem, where I think having an extra, like giving you here this whole 100 minimum of more than 100 times and all of this thing, and finding the minimum is just red herring. It is just there to confuse you. All you need to do is you need to plug in the numbers here and find if A and B both gives you an integer result, and then that's your minimum answer. And then you can use your 3A plus B to find the tokens that you will need for that. And funny enough, after solving this problem, I went on our Advent of Code, the subreddit, official subreddit. And good thing is people don't directly give spoilers there. So there are systems in places to do that. But there I got to learn that this whole thing that we did is called Cramer's law. And that is basically what helps you solve the whole, I was telling you, right? Like two equations with two variables, that is what it helps you to solve. And it took me close to 2 hours to get here and try to put this. And this was just a hunch. And that worked, that like I will just take like examples that are int and I will calculate, and I'll calculated the cost and I put it in the puzzle, and that worked. And I tried it for both of the test cases and there also it worked. So very interesting question, very interesting day. I definitely got to learn something today, and this was fun. I think last couple of days have been really humbling. And this is what I love about Advent of Code, right? Like it's not just about taking like graph solving equations and basic equations and doing that. It makes you explore different concepts around the coding. Like in this situation, I think this was linear algebra, which is very simple, like if looked from a distance, but can quickly get very complex for very high values. But yeah, so this was the day 13 for me. And I'm interested to know, like, how did it go for you? Were you able to solve it? Did it took you some time? Because part one was relatively very easy. And I think by having that whole less than 100 tries, the question tricks you into going into brute force, DP recursion kind of an approach. But then when you get to part two, it just becomes impossible to do it that way. And you have to basically write down equations and go back to doing your high school or like first year of engineering maths. It's actually high school math, but fun. Yeah. So yeah, I think I'm probably not going to record another video now. I was thinking of doing day 14 in a go, but it's 1:30 a.m. right now. And I definitely have to get some sleep. So what I'll do is I'll take off now for today, and I will edit this video and post it as early as I can. And then I will try to catch up on the day 14 problem. But this has been fun. I hope you enjoyed. And if you haven't seen my other videos of day 1 to day 13, where we go behind the scenes of a problem, how to solve it without even thinking about writing a code, do check out my playlist here. And yeah, like, share, and subscribe to me so that you don't miss the next 12 days that are left for Advent of Code. And do share the videos with your friends if they are interested in problem solving. And with that, it's time for me to leave. So take care. Bye-bye.